Okay, so certain amount of copper has a net charge of 2 microcoulombs. What fraction of the copper is electrons? So we're going to do some chemistry, and we're going to look up. Copper has an atomic number 29. That means there's 29 protons per atom and 29 electrons per atom. Has a atomic mass of 63.5. And so we're going to use that. And I'm just going to talk you through it. You're going to figure out how many atoms there's going to be. So we're doing like grams to moles to grams. Nope, we're going to stop to grams. It's going to go grams to moles, and then stop there. So that's going to give us 50 grams, and there's 63.5 grams per mole. And then we know that for every 1 mole, there's 6.02 times 10 to the positive 23. So we can figure out how many atoms of copper there is. And then we can multiply that by 29 because we know that there's 29 electrons per atom. Boom, the total number of electrons in a neutral piece of copper. Then we can figure out and say that we have 2 microcoulombs. We know that there is 1.6 times 10 to the negative 19th coulombs per electron. We can figure out how many electrons there are in 2 microcoulombs, and then take that number divided by the number of electrons that are total. And you know what it equals? Really, really, really small, like close to 0. So there it is. Sorry, Sarah. We just spent 15 minutes doing that problem. Whoop, 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 whoop. There it is. Nope. Yep. Yeah. Unit vector. That one. Okay. Correct answer here is D. Unit vector does not have units. Just a directional thing. Okay. So this is one way to describe. So this is the electric field created by that charge. Okay. You could write it like this, or you could write it like this. Sometimes people will write it like this because this is usually the bigger of the 2 charges, has a capital Q. They use capital Q and lowercase q interchangeably, kind of like they use capital M and lowercase m for mass interchangeably. Okay. Here is what I would recommend doing. This is how you would enter it into a computer program. If you want to include the charge, the positive and negative charge here, this will take care of saying, is it going out of positive or into negative? I think that's ridiculous unless you're talking to a computer. I would just forget the positive negative sign on the charge, calculate the magnitude of the electric field, and then figure out, is it going out or in based upon the charge of that. Is that okay? Assumption. So out of positive like sunshine, yay. Negative is like they're into themselves. They're like so self-centered, like That's how I remember it. There you go. It's a freebie. Aiden.
What is that epsilon on the bottom?
Yes. So this quantity right here is equal to K. Epsilon naught is 8.85 times 10 to the negative 12th. We'll see that a lot when we start doing calculus stuff. Okay. So it's yeah. Simon.
Do you need more vectors than just R for a two-dimensional case? Or is R like a polar thing?
I mean, you can describe it polar or rectangular, or I guess it's more rectangular. It's usually, but it doesn't have to be. It could just be a direction. And so if you go three-dimensional, you could do X, Y, Z, or you could do a spherical coordinates, which we're not going to get to.
Like 2 dimensions, but you need 2 vectors. Because you only have one there, but the picture is 2 dimensional.
Right. So this would be like 0.8, negative 0.2.
Okay.
And so you'd have an X component and a Y component.
Got it. Thank you.
You're welcome. Okay. So, yeah, I need to print out an equation sheet for you guys. All right, give that one a shot. Oh, I don't have a computer. Tell your neighbor. Correct answer is D, dangerous dinosaurs. Okay. This one's creating an outward directed field. This one's creating an inward directed field. We find the resultant of those two, and we get D. What's up? I'm about to do a chemistry reference. We just did chemistry. It's crazy.
Is it really chemistry?
It was legit.
I'm asking for questions.
It was legit. We actually broke out the periodic table and everything. I know. Tell your neighbor.
Oh, wow. That was a beautiful.
Okay, everybody good with B. Bouncing buffaloes. Okay, from the negatives going this way, positives going this way. It's closer to the negative, therefore it's stronger, and that field is going towards it. Okay, here's another chemistry reference for you. Ready? This is a, oh, I just blanked on the, oh, I know. Dipole. It's a dipole molecule. Is it? Yeah. Yes. Dipole. Isn't that or an adjective? I guess.
That's correct.
Okay.
Making sure I heard you correctly.
Dipole molecule. Okay. So it creates a field, an electric field that looks like add positive and negative. Yes. Okay. Dipole molecule. Very popular in chemistry and biology. Okay. So we have these electric field lines. I kind of just drew those out there. So the electric field is always going tangent to the electric field lines. the closer the electric field lines are together, the stronger the electric field. Okay, is this like last year? Like, yeah, kind of. Okay, James.
What determines how many field lines are supposed to put?
Beautiful question. It's all relative. So, like, if you have, so you start drawing them, and then you need to be consistent with what you started with. Does that make sense? So it's not a given. Okay. So electric field lines never cross. They go out of positive into negative. Yeah. Okay. So here, this is the equation for electric field of a point charge. What we already expressed. So you get outward, inward, dipole, molecule. Okay. So here, the electric field at this location is going to be that way, tangent to that curve. Here, it's going to be that way, tangent to the electric field lines. Okay. Thumbs up, and you got something in your brain. Everybody good with A? Okay, electric field lines are closer together. Therefore, you have a stronger electric field. Therefore, a stronger electric force. Therefore, a greater acceleration. Tell your neighbor. Okay, correct answer is B, bountiful buffaloes. To the right, to the left, cancels out. You just have going up to negative. Have a conversation. Okay. Interesting conversation, yeah? Okay. Trying to figure out which one to introduce to you first. Is it illegal for an object to cross field lines? So let's bring something where we are very familiar with, the Earth. Near the surface of the Earth, the gravitational field is doing this. Okay? If we have something on a cliff and we shoot it horizontally, we just crossed all sorts of gravitational field lines. Does that make sense? Okay, so it's not illegal to cross field lines. Now, initially, the force on this is going to go tangent to, that's the force, okay? And therefore, the acceleration is going to go in that same direction, okay? So it's going to speed up this way, okay, have an acceleration. Now, the force is going a little bit down like that, and it's getting stronger because, you know, they're getting a little bit closer together, okay? But proton has mass, it has inertia, it has a velocity going this way, okay? So over time, the force is going tangent, getting stronger, but our velocity is getting higher, like, and at some point it's going to cross over field lines because this has inertia. You all right with that? Okay. So C. How are we doing with there, conceptually? Okay. All right. That's electric fields. Electric potential. This has a this is usually requires a little bit more, like, we talk about stuff. All right. So electric potential energy. This is the potential for an electric force to do work. Okay. Ability for electric force to do work on a charged object or particle. Okay. Electric potential, these are just textbook definitions. When I was in your shoes, these made no, like, these were not helpful. But I'm just going to tell you to do it anyway. And hopefully bring you along and then look back and just go, yeah, okay, I get it. Electric potential is how much electric potential energy there is for every 1 unit of charge. Specifically, 1 coulomb. Conceptually, I try to look at this as, instead of 1 coulomb of charge, as per electron. How much energy there is per electron or per proton. For me, that just, I boil it down a little bit. That's not correct SI unit wise because per coulomb, but Gerald. Okay. I would describe this, so that's textbook. This is my home brewed explanation. Okay. It's the promise of electric potential energy to exist at a certain location. Remember our conversation with gravity. Okay, here, is there a gravitational force on the tennis ball? Yes. If I take this away and then I get rid of all air molecules, is there a gravitational force at this location? No, but there is a gravitational field. There's a promise of a gravitational force if I take something with mass and I stick it in here. Okay, so the field describes the promise of the force. You all right with that? Okay. Very similar conversation. At this location, does this tennis ball have gravitational potential energy? Yes. Okay. If I take this tennis ball away and I get rid of all air molecules, anything with mass, in this location, is there any gravitational potential energy? No. But what I can say is there is a gravitational potential. There's a promise of, at this location, there's a promise of gravitational potential energy if you take something with mass and you stick it in this location. How are you doing with, let me run through that again. There's gravitational potential energy. Take that away. There's no gravitational potential energy. But if you stick something with mass there absolutely will be. So what we do is say, okay, there's a gravitational potential. There's a promise of potential energy if you take something with mass and you stick it there. We have the same exact conversation. Instead of gravitation, we put in electric. Okay, we have. Let's pretend our trash can is our Van de Graaff generator, big silver shocky ball thing. Okay, and this is a charge. This is like our charged peanut, packaging peanut. Okay, at this location, is there electric potential energy? Whether this is charged, whatever it is, it's either going to be attracted or repelled, but there's potential energy there. If I take this away, is there any potential energy in this location? No, but there is electric potential. There's a promise of electric potential energy if you take something with charge and you put it in this location. It's how much energy there would be per coulomb. How much energy there would be per electron, proton. Okay. So electric potential difference is simply the difference in electric potential from one location to the next. Okay. This, though, is voltage. And that concept here, we'll use that the entire semester. So like, that's a simple explanation, but this is the single measurement that we'll use the whole semester with circuits and electromagnetism. Okay. Good. All right. So if we have let's first look at gravity. Gravitational potential energy looks like this, right? Okay. As you get closer and closer together, you're decreasing potential energy, but we're going more in debt. So we're going away from zero, less than zero. Good with that? Okay. It'd be nice if we taught this first because this would make more sense. Okay. Where do you have more energy if you have two positive things? Here, more potential energy. Here, closer together, or here, farther apart? Where's there more potential for electric force to do work? Closer. Okay. As you go further away, you decrease potential energy. Okay. So this is for repulsion. This is a scalar quantity potential energy is. So we're going to include the signs of the positive or negative. We're going to include the signs of the charge. Okay. If they're both positive, this is positive. If both are negative, this is positive. If one's positive, one's negative. Ooh. Okay. So this is repulsion. Two positives, they're close together, there's more potential energy. As you go farther apart, there's less potential energy. Good? Okay. If you have a positive and negative, where is there more potential energy? Here or here? Farther apart or closer together? Farther apart, there's more potential for force of attraction to do work. Okay? And so, I forgot a really important thing. Where would be, for repulsion, where would be there be zero potential energy if they're repelling each other? Infinitely far apart. Does that make sense? So, in order to make this a complete story, we need to start from far away. That's where there's the most potential energy if there's attraction. And as they get closer, we decrease potential energy. So we do that thing. For potential energy when something's attracted. And guess what gravity always does? Attracts or repels. It just pulls things together. Come on, let's get. Okay? Get in here. You know you. Okay? That's the only option that gravity has. It's attraction. All right with that? Okay, how are we doing with that? So, big takeaway. Include the signs of the charges because this is a scalar quantity. For a vector quantity, I would ignore the signs of the charge, figure out the magnitude, figure out the number, and then use your brain to figure out the direction. Okay? So, if we're starting here, like charges, and we're coming here, our potential energy starts way here. So this is not chronological. This is distance. We start far away. And, oh yeah, okay, that's important. We're shooting them at each other. So they have a certain velocity initially. There's kinetic energy. Okay, so there's a certain amount of potential energy. There's a certain amount of kinetic energy. And then I guess we worked backwards there. So they shoot them at each other. They stop right here. So you have a maximum amount of potential energy, the blue curve. Your kinetic energy is 0. Therefore, your mechanical energy is this. Because it's a conservative force. Electric repulsion and attraction are a conservative force. Good with that? Okay. And if we are we're attracting each other, we shoot them away initially, and at some point they come to rest. So this is where they come to rest. So our kinetic energy final is 0. This is how much mechanical energy we have. And so right here is our initial position with a certain amount of kinetic, like here's your mechanical energy, here's your potential energy. You can figure out your kinetic energy from those two. Sure. Say that again.
Can you go back a slide really quick?
I sure can. So here's initial where they're moving. Your finals are closer and they're stopped. Okay. Here's another interesting point. Mechanical energy is positive here. Mechanical energy is negative here. Good with that? Okay. All right. Correct answer is, tell your neighbor. Okay, so this is an interesting conversation. So the question that comes up, are you talking about magnitude? And I was like, no, because energy doesn't have direction. Okay, so if I say, so like a temperature reading, if I say -5, and you're like, do you want the magnitude only? I'm like, well, that totally changes things. You're like -5 versus +5 versus 5 meters per second a vector going to the right versus 5 meters per second going to the left. Does that make sense? So you don't really want to say a magnitude of a scalar. You could say absolute value of a scalar, and I'm not asking for the absolute value of a scalar. Okay, so that's one side comment or side point. The other side point is the simplistic answer is, well, it's that because it's positive value. But I want to dig just a tad bit. If left to like unhindered, which one do you think is going to have more kinetic energy at the end? Like this would be before they collide. Which system, this system or this system, is going to have more kinetic energy? I should have thought about this before I asked the question. I'm going to venture to say A is, just because there's a whole lot more distance.
You're going to go from that to infinity.
Right, this is going from this to infinity. Now it is decreasing off, like at r, like 1 over r squared, like it's inverse square law. The force is proportional to 1 over r squared. Potential energy is proportional to 1 over r. We could figure this out with calculus. Probably should before I ask this question. But they were okay with that. Like looking at it from a kinetic energy point of view, that kind of scratches the itch of, hey, are we talking about the absolute value or not?
So from setting to like, I don't oh no, I got it.
You go with that?
I got it.
Yeah.
Would they both be approaching infinity? Or like, so that, like,
No. Okay. Good question. Good question. So this you would have to take into account the radius.
hey, what?
You'd have to take into account the radius, like
Okay.
when they hit.
Okay,
So
so,
when
we
we
are,
do-
okay.
So when we did that with asteroids or stars with that lab, I had to give you a radius because otherwise you're dividing by 0.
But then, like, how do you know when, because, like, that one you have a stopping point, like,
Yeah.
when they fly, but the other one,
It's infinite, infinity. Like you make that infinity.
okay.
So I'm probably gonna sit down and actually solve this. But like an electron and a proton, and the radius is of I don't know. Homework assignment is forthcoming. You too. See you.
So is like